we can make it official. Happy Garbage Day. It's a lovely fall Tuesday. Who's doing trick-or-treating on Friday? We got our costumes ready? No one? No one has to go trick-or-treating? I'm pretty sure I'm going to get stuck on either doorbell duty or walking my kid around the neighborhood, and I'm not sure which is worse. But doorbell duty is definitely lazier. Just park a chair next to it and be like, here you go. I have done that before. The ultimate laziness is you dump the candy in the bowl and you leave it on the porch and you're like, good luck, kids. Yeah, well, within 5 minutes it's gone is the problem, it seems like. But who am I to care? Yeah. Well, if you want to take your kids out trick-or-treating, you can't be in two places at once. So that's what we're going to do. I don't have a costume. I gave up on that a very long time ago. But my favorite costume I ever did was I was a runner who got hit by a car. And I had like running clothes and I made them all dirty. And then I got a tire and like rolled like a tire over my back like with black paint. I made a head injury out of marinara sauce. And I wore that costume to the restaurant I worked at where I got the marinara sauce. So I did. Yeah, good times. Anywho, statistics? Is that better? What are we even talking about? We got to get ourselves reoriented here. What do you remember from like 10 days ago? Nothing? Swing and a miss? Okay, let me start before that. What's this class about? I'm watching the Zoom windows too, Zoomers, if you want to chat with me or talk. What's this class about? What are we doing? No wrong answers. No one wants to talk. Yeah. Yes, general linear models is what this class is about. What are they for? What are they used for? Determining linear relationships between outcomes and predictors. I'll take that. What kind of outcomes? Predicting outcomes, good. What kind? Yeah, numbers. Yeah, things that are plausibly continuous, right? There are regression models that are designed to predict not normal outcomes, but that's a different set of concerns. It takes everything you learned this semester and adds more to it, though. So don't think that you are wasting time if you have categories to predict instead. Do the relationships have to be linear? No? Could the lines become bendy? Sure, we can do that. We have seen a couple examples of that. In your last homework, you had a quadratic effect of a predictor. So if you put in the predictor and the squared version of it, that creates some kind of bendy line. Usually it is the shape of like either a full U or half a U, either one. What about analysis of variance? How does that fit in here? Can you do that in a general linear model?
Yeah, it combines multiple fixed slopes to look at the difference between groups.
Yeah, if you have a categorical or grouping variable as a predictor, and if you have, say, 4 categories, how many slopes do you need? Y'all did this in your homework, 3, yeah, because the 4th one is essentially determined by the intercept. So you set one of the groups to be the reference group in a typical coding scheme, and then each slope gives you the difference of another group relative to that reference. There's another coding scheme that we looked at the very end of the last class, which I will go back over as promised. What if I had 5 groups? How many slopes do I need? 4, yeah. So in that case, I would have 4 differences directly given by the model, but there's several more that I might be interested in. Am I out of luck, or can I look at those too? I can. If the model tells me how each group gets its own mean, then the model tells me how the mean differences work too, not just the ones for that. So this unit, I would say like the theme, is we started with empty models, right? Like no predictors of any kind, and the variance in an outcome is all the variance that's there. And then we added one slope to get used to the idea of building a model and looking at the estimate, standard error, significance test, effect size, all that good stuff. This unit is focused on still the idea of one predictor variable at a time, but in which it takes more than one slope to fully specify how that predictor relates to an outcome. That's the conceptual here. Let's see, what's F? Capital F. It is a test statistic. More generally, F is a test statistic for multiple slopes at the same time. A special case of that is when you're testing your model and you want to know if all the slopes in your model work together to predict an outcome. What's an effect size that goes along with F as a significance test? Another capital letter. R, with a number after it? R square, yeah. That is variance accounted for. By what proportion has the overall variance in your outcome been reduced after putting in your predictors? If I wanted to talk about R instead of R square, how could I do that? Yeah, unsquare it, that's step one, but then like, how do I think about that in terms of a model? How do I talk about model goodness using correlation as language? That's what I'm asking. Cheers. So if I want to correlate Y with something to talk about how good my model is, what is the something I'm correlating Y with? Oh, this one's a tricky one. Do we go back over it?
Changes in group.
Not quite changes in group. So Cohen's D, the Zoomers say that's an effect size for standardized mean differences. If I want to talk about model R square and I want to use the word correlation in the sentence, how do I do that? That's my question. Do we need to talk about this more? Re-go over as opposed to review? Did that help? I'm sorry, I can't quite hear you. No, you're like, no, I withdraw my answer. I'm good. All right, fair enough. Let me find where this is here. We'll talk about that for a second. Okay. So this big table here, this is slide 14 in lecture 3. Or it used to be. There we go. So this is what is known as a sums of squares table. And in regression models for normal outcomes, you will see this type of table. In any other kind of regression model for not normal outcomes, sums of squares is not a thing because the model is estimated using a different standard, essentially. But we have in this thing right here, this column right here, sums of squares. And here's the little formula that builds them. This one is y hat minus y bar, right in here. This one is how much information did you introduce by adding in predictors in the predicted outcome. So like where you start with the empty model is everybody gets the mean as their predicted outcome. That's y bar. And then to the extent that you've added in predictors, that causes variability in the predicted outcome. That's y hat. So this is asking like how much more information do your predictions have because you've added these predictor variables to your model. Residual, and what's a synonym for residual? Starts with an E? Error, yep. Error or residual, depending on your software package. This is your original outcome y minus y hat according to the model. So this is how wrong you are. So this is like how right you are, this is how wrong you are. You put it together, you get all the original information back. Next column over is degrees of freedom. How many slopes did it take to capture that much information? How many slopes could you still add to capture the information that remains? And so then this divided by that becomes mean square, residual, and model. Then we have R square is built using these two sums of squares. That's one way to talk about it. The other is that it's how correlated y hat is with y. So it's not the correlation between like group as a variable and y as a variable. It's the correlation between the y's that group creates and the original y's. Because group takes at least 2 slopes to differentiate the groups, more so the more groups you have. So that's another way to think about what R-square means, is that it is a measure of how correlated your predicted outcomes are with the real one, but just squared in that case. So you can think about it either way, proportion reduction of error or this thing right here. F looks like that. Okay, what else do we want to talk about as review? Back out of this here. What things come to mind that are swimming in your head like, I don't know what that is still? Nothing off the tops of your head? Not right now? Okay, we'll wait back in. That's all good. So then in terms of examples of situations in which you would need more than one slope, we walked through nonlinear trends. So here's some pictures that might jog your memory. So these are different flavors of quadratic trends. If the signs are in the same direction, then the curve is speeding up. If the signs are in opposite directions, the curve is slowing down. And those are the words that I tend to use. Like in this picture, the positive slope is becoming more positive, and it's always by twice the quadratic per unit of the predictor. Here, the positive slope is becoming less positive. So I would say the effect is getting stronger as you move up x in this picture. It's getting weaker as you move up x in this picture instead. And the same is true with the opposite directions down below. Let's see. We did an example where we fit a quadratic model for this. That worked pretty well. This is the kind where it truly is a parabola type of shape, and a linear model would not make a lot of sense. We did piecewise. That was the last time we talked, I think. What's the objective of piecewise models? When would you use these? Here's an example of one.
Change between your groupings is not distance.
That's one reason. When you don't want to assume that the difference between successive values is the same. So like if you have an ordinal predictor, for instance, that's the last example. In this case, we have continuous education, but we're carving it up into 3 different regions and fitting a separate slope through each region. So piecewise models are useful when, like in a longitudinal setting, like if time is your x variable and you know something happened, like COVID hit, a hurricane hit, hypothetically, right? There's a giant change in administration or laws or other kinds of policies. Like there's a discrete separation, and you want to know what happened before and after. In these types of continuous variables, if there are regions that define qualitative distinctions, like someone who has clinical depression versus subclinical, you can carve up a depression measure into regions and look at how being more depressed affects some outcome among subclinical versus clinical. Like you can have separate relationships like that. So it's kind of like fitting a nonlinear trend, but in a different sort of way. The example that you are thinking of with the slopes is this one. So this is an example with a ordinal predictor of happiness. It's measured on a scale of 1 to 5, but we can agree these aren't numbers, right? So in this coding scheme, this is slide 38. I'll take this up here. Come on, there you go. This is not the same coding scheme. In your next homework, you will get a chance to practice this one instead. This is a coding scheme that is designed to represent adjacent differences among successive categories. So rather than resetting each of these slopes back to 0 when it's the other groups, we keep it at 1 so that we create this sort of like stair-step function where each slope then picks up where the other ones left off. And logically speaking, if the difference between 1 and 2 in an outcome is the same as the difference between 2 and 3, is the same as 3 and 4, is the same as 4 and 5, you've built yourself one line. And so it's like saying, no, I'm going to treat this as a number and fit a linear slope through it, because each of these successive differences is sufficiently equivalent that that makes sense to do. So to me, anytime you have an ordinal predictor, it's an empirical question, whether you can pretend it's a number and put a slope through it, or whether you need to pay attention to each of these differences potentially not going in the same direction. Here, it looks like we go up, and then we go down a little, and then we go up a little, and then down a little. So a linear slope wouldn't make a lot of sense given this pattern. So here is then the alternative version of a coding scheme, which is more suited for nominal variables, where you have one reference and each slope pulls a subsequent group off of that one reference. So here's what happened with the happiness variable. Each of the slopes was non-significant and all of the slope differences were non-significant. Therefore, you could fit one line through it, but that line is flat and we don't care. So we had walked through some code that did all of that, and I think that was about the end. Okay, my question for you, do you want to walk through the code that does these things, or would you like to move on to something that is the next topic? Multiple predictors at the same time. I can't hear you. Code. You want to look at some code? Get back in, get our heads like back in this? Okay, that's fine. I suspected as much, which is why I got this open already. So this is the example syntax and output that goes with all of the results that are in that PowerPoint. So this is basically, how did I make these numbers come out of the computer? That's what I want to be able to show you. Do you want to go back over the first two examples that were just, that your homework was just dealing with, or do we want to look at just the last two? Last two, we're good on that? All right, cool. All right. So descriptives, all of that. Working class, we did that. We did group differences and effect sizes. We did quadratic stuff and effect sizes. Right. Piecewise. Is this where we should start? Why not? Okay. So this is the code and output that goes with these ideas right here. We are taking a numeric predictor, carving it up into regions, and fitting a separate linear slope through each of the regions by creating 3 new variables. And this coding scheme is designed to make grade 11 the reference for the model as the intercept, because that is the point where all the new predictors I'm building are 0. So we know that that is then going to be what the intercept predicts. When all the predictors are 0, the intercept gives you the expected outcome. We know that will be for 11th graders. The first variable that I am creating, the idea is that I want to measure how far away you are from 11 on the low side only. So in this sample, I think it's 2. Yeah, 2 is the lowest one, maybe. So anywhere from 2 to 11. That's what we're tracking. Given that I've already coded 11 as 0, 10 is 1 less than 11. 9 is 2 less than 11, so that's why it's going backwards. After 11, though, this variable is agnostic. It's not in charge anymore. So it gets zeroed out because that's where we left off. It's like a relay race. The next variable kicks in where that left off to move us from grade 11 to grade 12. Because graduating high school, in the data, looks like it's associated with a very prominent difference. So I have 11 to 12, and now it shuts off after 12 at 1. Then the third relay comes in, and we have how much further than 12 your education is. So that's why it starts at 0, because we get to 12 with this one. Now we pick up where 12 left off, and we have 1, 2, 3 in terms of moving forwards. So this is the slope for this section of the data. This variable tracks the change in years of education that will be given a slope, I should say. This one is going to track the change in education from 11 to 12, and then the last one is after this. Okay, is the logic clear on that? Zero in this case means they're in 11th grade, so they do not have a high school degree. Yeah, and that's an arbitrary, like you have to pick somebody to be the 0 group. I thought it would be useful to have it near the middle. And the ones, yes, because this is only trying to cover people who moved from 11 to 12 and give them a difference. So it's kind of like I have groups in the middle, I have numbers before and numbers after. You can kind of think of it that way. Does that help? Maybe? I'm trying, at least. I'm trying to help. So to execute this, then, in both packages, the same process, I am writing functions that fill in these tables. So you could write code that says, like, if it's 9, do this, if it's 10, do this, if it's 11, do this, but that's inefficient. And it may take a very long time if you have a lot of possible values. So here, I am making code that, for instance, subtracts 11 off the first variable to create this. It subtracts 12 off the last one to create this. And anywhere that there's supposed to be a zeros, I've assigned those. So for instance, if it's less than 12, make it 0 for this column and for that column. And then if it is less than or greater than or equal to 12, then make it 0 and 1 for these ones up here. So I would highly recommend building a table like this first anytime you need to do this. So then you can figure out if your code is actually doing what it should. It may take a few tries. It's a little tricky sometimes, but that's okay. In Stata, you read these sentences backwards. So if education is less than 12, then replace it with this function. Same idea. It's just in a weird order. So here's my model. So how many predictor variables do I have conceptually? Like if I were writing a research question about this analysis, what would it be? Can you think of one? Ultimately, that's what we're here to do, right? Formulate and answer research questions and make the world a better, more informed place. So what would an example research question be that this model answers? How is income related to having a high school degree? Yeah, I think you could start with like a more general sort of how is income related to education level? And then more specifically, is there a, let's go with salient benefit of graduating high school? There's some GRE words. Yeah, like at its highest level, the question is, does education predict income? But then it's like, okay, how do we specify education? And in this case, we're using this 3-piece function to say, is there an effect of education among those who have not graduated? Is there an effect of education in comparing 11th grade to 12th grade? Is there an effect of education among those who already have a high school degree? So you can almost think of it as like a moderation type of question. You're asking whether education matters to the same extent in these different subgroups of people as defined by where they are on the education spectrum. But one variable conceptually of education that takes 3 slopes to describe how it relates to income. That's the bigger picture on that. Let's go to the R output for this. How folks who are learning R for the first time, how is that going?
Not as bad as I thought.
Not as bad as I thought? Yeah, that's good. I found that R can be very challenging because it breaks for reasons you're not sure. And like the error message, you're like, I have no idea what this means. The Google can help with some of that, but to me that's the hardest part is trying to diagnose error messages. Stata is not much better, to be honest. It gives you messages like, this is error code 504. Like, thank you. And then you like click on it and it gives you 87 reasons why 504 could have shown up. Question?
No, just a comment that if you're using Stata, don't get too deep
That's true too.
And just, I just make sure it happens to other people.
Yep. The Zoomers say it is teaching me to be extra careful when rereading. Amen to that. Yes, indeed. Yeah, so it does get better with practice, but I'm not going to say it's ever like fun. No. not going to say that. But I've tried to make it as least painful as possible. So Supernova is the function that I found. There's a package that creates this table right here. So in this case, I have 3 numerator degrees of freedom because I got 3 slopes in my model. This F is my test statistic, asking me per slope, how much information did I capture in my model relative to per slope, how much information is left over. Essentially, did I get a good deal, so to speak? Did the slopes I put in do better than any average slope that isn't related you would expect to have? What's this right here?
Proportion reduced error.
Yeah, proportion reduction and error, otherwise known as what in this class? Yeah, R squared. This is like an author-specific term that they invented. P is 0. Is that good or bad? First off, is P actually 0? It is not. It is 0 to 4 decimal places. It's always going to be some eventual number. It's not actually 0. In this case, it means that we would achieve this level of prediction of 16% of all the variance in income less than this proportion of the time if there really were no relationship between education and income. So these results are highly unexpected if the null hypothesis were true. What's this number right here? It's a variance, but which kind? Variance of what?
Residual variance?
Residual, yes. Leftover variance in the outcome variable. What's this number down here? I don't normally ask about that one. It's also variance. The total. Yeah, this is the original. So 190 is how much variance we had in income to start with. 159 is what we're left with. This is by how much it went down. So you got the whole picture here. So I made you estimate empty models as more of a pedagogical exercise and recognizing like that's the naive starting point for your prediction. The variance that they would give you is right here. So you don't actually have to have that as a separate piece of information. Slopes, do we want to practice interpreting slopes? So my intercept here, given my coding scheme, this is for 11th graders. 11th graders are predicted to make $8.5 thousand per year. Do I care that this is significant, the intercept? Does that matter to me in this context? Would that make it into my results section? What does this p-value mean specifically when it's for the fixed intercept?
That your intercept is not 0.
Yeah, that the intercept is not 0, meaning the average income level for someone who has 11th grade education is not 0. That's not part of my results section. The only situation I can think of in which that would be something to report is if 0 were a meaningful reference point on your outcome and you want to say that some expectation is different than that. The examples I'm familiar with are like feeling thermometer things, like on a scale of like -5 to 5, how do you think about something where 0 is neutral? And you might say, oh, people with this characteristic are significantly different than neutral, something like that. You might want to make a claim like that, but that's the only circumstance in which I can see this being useful. Does education matter if you don't have a high school degree? Matter, right? That's a subjective opinion. Let me ask the question more specifically. Is there a significant relationship between education and income among those who do not have a high school degree? Yeah, p-value of 0.65. meaning the slope is estimated as negative 0.27. So as education goes up, income goes down. It's actually backwards from what we would expect. However, the expected inconsistency of that slope, of a sample slope relative to a population slope on average, is 0.6. So this slope is closer to 0 than we would expect any random slope to be. So the t-value then does not go outside the boundaries of plus or minus 2. We would expect to see a slope this big or bigger 65% of the time if the slope were actually 0. So it's well within expected territory. If you graduate high school, does that help your income? Yep, significant increase according to an alpha level of 0.05. What if I said, no, I want to be extra conservative and my alpha is 0.01 instead? Then what do I say? It's not significant anymore. 0.0127, not less than 0.01. Approaching significance. It's trending. It's marginally significant. No, there's like hundreds of euphemisms for not quite significant, but I'm going to talk about it anyway, damn it. You can see why this is supposed to be a decision you make ahead of time, as opposed to once you've seen your output and you're like, my alpha's 0.03 today. Like, that will just get me everything I want. Yeah, no. They call that p-hacking. There's a term for that. Or what is the other one? It's like there's like a new questionable research practices, QRP. There's an acronym that has come into vogue. That's like when you're trying to say your PIs are cheating, but without saying that directly. If you have more than a high school degree, does more help you? Yes. So this slope is decidedly away from 0. It is unexpected, sufficiently unexpected. It is almost 10 standard errors away from 0. So we would say, yeah, that's well within unexpected territory. So the next table here adds effect sizes. What are they for? In a general sense, what is an effect size for? What's its purpose? Making a reviewer 2 happy is one purpose. Making your advisors happy is a second. What's an effect size? You know 2, R&D. So we've decided that this slope is significant, right? It's 2. Is that a really strong relationship? It's $2,000 per year. Like I'll take it, but like what would like the strongest possible slope be given the scale of these variables? I don't know. You could probably figure it out with some math, but it's not intuitive. So I can say that this slope is not 0, but I can't like explain it in any kind of layman's terms, like how related are these variables? Because this 2 is because we're talking about $1,000 units per year of education. You got to know that part to know what 2 means. The idea of an effect size is to take away the units. Like this column right here is an effect size that's known as partial R or partial eta. Actually, you'll see that more commonly, that word. And these are in a correlation metric. So I can compare, I don't want to compare the intercept, but like I can compare this one and this one. Even if they're in different units, I can say, oh, 0.34 is a stronger correlation than 0.09. How strong do the correlations go up to? What's the best it can be? 1. How about -1? That's equally strong. So the sign follows the sign of the slope. But this is a way to try and convey in a more absolute or standardized way how useful this predictor is in the model. And you don't have to know what the units are to be able to evaluate that. Cohen's d is another effect size. It also belongs to the partial family. That's a distinction that comes in the next unit. These are standardized mean differences. So Cohen's d is more intuitive when you're talking about a predictor that reflects a grouping variable, and you can talk about this group versus that group. In this example, only graduating high school is like that. It's functionally a binary variable because it's 0 to 1 when you switch from 11 to 12. So I can say that folks who graduated high school are different from folks who only made it to 11th grade by 0.18 standard deviation units. That's how far apart those two groups are. If you don't have groups, Cohen's d isn't going to make a whole lot of sense. But the function that I wrote to compute these things spits them out for everything. It's up to you to decide which ones you want to report and talk about. So the columns of this little table here are designed to be something that you can directly put into a manuscript. You would want to report estimate and standard error at the minimum. Do you think you need t? I don't think so. Do you know why? Because t is this divided by that. Your readers can make a t if they really need to. So that's one reason I don't think you need t. The other reason I don't think you need t is because t is a means to an end to get p. Right? That's what people want. So you can either make a p-value column or you can do stars. So in R, for instance, the LM function defaults to including stars for various levels of significance, and my example code turns that off because I find it annoying. But you can turn it back on if you'd like. What I will say, though, is try to reduce the urge to sit on top of the fence. By that I mean 1 star for p less than 0.05, 2 stars for p less than 0.01, 3 stars for p less than 0.001, like that kind of thing. Like, no. Significance testing is supposed to be a binary distinction. If you want to make those gradations, I would just put in the p-value column. So these two things, estimate and standard error, would get you the t, they get you the p. Then effect sizes are nice to include as well, and you can pick whichever one would make the most sense for your situation. How about confidence intervals? Do I need those? Depends on the journal. Some journals insist on having confidence intervals, but how are these things built? Yeah, this plus or minus roughly 2 times that. So again, if you provide them with these two columns, they can make the confidence intervals. Those are really the only two unique pieces of information that you need, estimate and standard error.
So really the backhanded way to get your reviewers to do more work.
Some places are like, we do not want p-values, we want confidence intervals. It's like, okay, it's 6 of one, half dozen of the other. The fact that this p-value is significant is also evidenced by the fact that this interval does not include 0. The fact that this p-value is non-significant is evidenced by the fact that this interval does include 0. Take your pick. Slope differences was the other thing that I had in this example. How you can contrast adjacent slopes to see whether they do need to be separate or not, and it looks like in this case it might be a little bit ambiguous. The first one does not need to be, but the second one might. Then we did happiness as another example of a piecewise model. Do we want to do that one too? Maybe? Sure, why not? It's like, I'm here. So the straw man argument is first, a linear effect of happiness. My happiness scale is measured from 1 to 5. So if I just put in happy as a predictor without centering it, my intercept would be for people who answered 0 on a scale of 1 to 5. So that's weird. I'm going to center it at the minimum value so then I can talk about as happiness increases, this is what happens to your predicted income. Let's go down to, actually, nope, I don't have that output in here. Here we go. This is it right here.
Can I ask a quick question?
Yeah.
Back to the education.
Sure, let me scroll back.
So, looking at this image right here,
Mhm.
this table, so what we're predicting as our slopes are these dotted lines, correct? Like fitting, that's the slope that we're fitting to that area.
Correct. So this
Okay.
picture is illustrating what the model predicts. And then the red dotted lines are the standard error,
Yeah.
like,
Okay, perfect.
Yep.
Just wanted to clarify.
yep, sorry, should have said the quiet part out loud, but I
No,
did
it's
not.
okay. Thanks.
Yeah, and that is, so that's a convention that I follow and that I've seen, like, when you're showing predictions that use the dotted lines, but then you're showing like what actually happened, it's the solid lines, because the prediction is like hypothetical through that. But yeah, this picture tells me that the rest of the model from 12 to 20 is not very well specified, because it looks like this is not a straight line. So it kind of looks like you need separate pieces for each of these things, but that would be a little bit overkill. Okay, other questions? Yeah. Ah, so that is a discussion that's coming in the next unit, but I will answer the question now. Let me get back to where we are here. Hang on. Here it is. Okay. So standardized slopes. In the situation in which you have only one slope in your model, like one predictor, one linear slope, that's it, the standardized slope, as it is known, is equivalent to a Pearson correlation. And a standardized slope uses the standard deviation of x and y essentially to strip off the units, so that then a standardized slope in that instance ranges from -1 to 1 because it is a Pearson correlation. Okay, cool. Everything's good with that. The same logic can be used to create standardized slopes in these kinds of models as well when we have more than one predictor. However, I don't like them. The reason is because they don't actually range from -1 to 1. They can go outside of bounds. Because, again, this is the next unit, so what I'm about to say makes no sense. You can just be like, I want to listen. But if you've heard of these things before, then it's fine. In models that have more than one predictor, each predictor only gets to take credit, so to speak, for the variance that it brings to the prediction that no other predictor did. Like its unique effect is the idea. That's where we're headed next, is where predictors are like battling it out to see which one is the most important. And in that situation, the standardized slope still uses all of the original variability in the predictor as the basis for standardizing. But really, what the slope represents is only the contribution of the unique variance in the predictor. So there's a mismatch there, and that mismatch leads to things going out of bounds. So I don't like standardized slopes because I don't think they reflect what's actually happening in terms of what the slope means. Because it depends on how related the predictor is to the others, like how much overlap it would have. The other problems with standardized slopes is that they change with orders of operation. So let's take the quadratic slope, for example. Let's say that I wanted to have, let me go back to that picture, it's in here somewhere. This picture, age and age squared. If I create a standardized version of age, like I turned it into a z-score, and I square that z-score, I do not get the same thing as if I take age, square it, and then turn that product into a z-score. So they don't match. And then it's unclear which one is the right one because you have different definitions of what 0 means. Standardized slopes also in binary and categorical predictors, they depend on the relative differences in sample size across the groups. And you can get a different effect size as a function of having unequal group sizes. So that's why I don't like standardized slopes, and they're not part of my story. But if you're like, my advisor wants standardized slopes, you know what you do? Add a column. Don't fight that fight, right? Just make your table bigger. It's like, well, I will add, instead of Cohen's d, I'll stick standardized slopes in here or something. There, long answer to a short question. Did that help? Okay, it's coming later though. That rant will be featured again, probably not Thursday, but maybe next week. So you'll get to see it again. All right, so what are effect sizes for? conveying size of relationship in units that make sense to people. They are also used in planning subsequent research. So this is what you're supposed to do in planning new research, is to go to the literature, see what effect sizes have been found before, and then try to design a study that has enough people to have a good shot at detecting this effect if it's really there. Good shot is statistical power. That's the idea. What proportion of the time would you find this if this is the true effect in the population? However, how precise this effect size is determined by sample size. So really what we should have is a confidence interval around these effect sizes too, because it's not perfectly 3-4. We know that. So the more people you have, I think the more faith you can have that this is a good estimate of an effect size, but the more people you have doesn't make it larger. That's, I think, a common misconception. You can have a giant effect size in a small sample, but then you really don't have a good sense as to how giant it is. Any one person can throw it off more so. So effect sizes are used in study planning. They're used to convey unitless types of relationships between things. And it's also used as an argument against, well, you have null results because you don't have enough power. Like, well, I can compute after the fact what my power would have been for this model and argue on the basis of that. So effect sizes are important as supplementary information beyond significance. Ding, ding. All right. Okay, happiness, not buying money, not buying happiness with money, that kind of thing. Okay, so more review. If I just have one slope, a linear slope here, then the standardized version of this beta 1 is going to be a Pearson correlation. In this case, do I need to pay attention to the significance of the model? Here's the results from Stata this time, since I've been doing R lately. If I have one slope, do I need to worry about reporting an F-test per se? What do you think? What about this t-test right here? Are these numbers related to each other somehow? They are. T squared is F for one slope. So this is telling you the same thing in squared units as unsquared units. So if you only have one predictor, the F-test for the significance of the model is the same thing as the t-test for the significance of the slope of that one predictor. The correlation effect size that you would get for this one predictor's slope, if you square that correlation, you would get the R-square for the model. It's one-to-one correspondence. So that's why in your initial homework, I said you could ignore this table because it's not going to help you anything. It's not going to add anything. So for every additional unit of happiness, income goes up by 0.7 non-significantly. Here's a plot that shows what the model is predicting. So it's a linear slope. Even though we go up, we go down, we go up, we go down. Doesn't make a whole lot of sense in this case. So if we do the ordinal version, which includes these piecewise slopes instead for adjacent differences, then we can examine the effect of each one in turn. Okay, let's see here. How many fixed effects are in my model at this point? How many fixed effects? Terminology review. Should the last one be 4?
It should be 3.
Oh, yeah. Good catch. I think I've given this handout at least 4 times, and you're the first person to point that out. So good work. Yeah, I got 5 fixed effects. I have a beta 0 fixed intercept, which is what I always start with, and I have 4 slopes for these differences. So in this case, the test of the model is not the same as the test of each of these individual slopes. The test of the model is how well they work together. So this is a different result than what we've seen up to this point. Make that bold. So here's my sums of squares table for the 4 slope model of happiness. So degrees of freedom 4, because 4 slopes. F is 1.2 with a p-value of 0.29. What's that tell me? It's not related. Happiness, as specified using 4 fixed slopes, does not significantly predict income. I did not get a good deal at the statistics store. I added 4 slopes to the model that would have done just as well as a bunch of random stuff, random 4 things. And those 4 slopes explained less than 1% of the variance. So here's the solution that provides the adjacent differences. The intercept given my coding scheme is going to be for happiness equals 1. What does this variable represent? It's 1 versus 2. 1.68. What happens to that number? Yeah, if I answered my happiness at a level of 2, I make a little bit more money, but not significantly. Relative from 2 to 3, I make less money. 3 to 4, I make more money. Marginally significant. So here's the thing. Like you'd be like, but this p-value is significant. So out of the 4 slopes, only 1 is significant. F is a per slope measure. So if you have 1 good slope and 3 crappy ones, that's going to like bring your per slope contribution down. So you can end up with predictors that have significant slopes in the context of a non-significant model because you've got extra crap in there you don't need. That's my scientific explanation. And then we have 4 versus 5. What if I wanted to compare 1 and 5? Could I do that? I could. I'm going to have to work a little bit to do it, though. So in your previous examples, to compare non-reference groups, we take one slope and subtract the other. But this coding scheme would actually render that different. This coding scheme, get to the table again. Here we are. This coding scheme is a relay. So if I want to get from 1 to 5, I need all these. So I would have to compute the mean as given by all of these things, and then minus the mean as given by 1. So the coding scheme that you use directly dictates how you would form linear combinations to make things that aren't directly given by the model. But as long as you can figure out what the predicted outcomes are for any combination, then you can figure out what the differences are too. It's just a little bit trickier. There. So at the end of this then, I would say no, happiness is not related to income either as a linear slope or 4 sequential ones. And that will be the end of the story. There we go. All right. The end of the handout. Not that one. This one. There we go. Yeah, that's it. We really did. We really made it through. So, summary. How about we do the summary slide and we go home? Deal? Start the next unit next time? Yeah, I think so. So there are many situations in which you want to take one conceptual predictor and have it predict an outcome, but you need multiple slopes to do it. So for instance, if you have a categorical predictor of C categories, you need C minus 1 fixed slopes to distinguish its C different outcome means. 2 different coding schemes I showed you for doing that. There are more. There's plenty of others. You should report significance and effect size for each of the mean differences, not necessarily all the ones that are possible, but just the ones that are interpretable. So for instance, in the golf homework that you would have just finished, I didn't ask for all possible comparisons. I asked for the ones that would have some kind of direct interpretation. Another situation in which you would need multiple predictor slopes for one variable is if you want to make bendy lines, so quadratic, piecewise, etc. And for each fixed slope, we want to know its significance and effect size, but we also want to know for the overall model its significance and effect size too, and that's F and R square. For each slope, that's T and then some kind of effect size, either a D or an R, and that's where we're at. Okay, so where we're headed then is the idea of building predictors simultaneously to make them fight it out. Questions like, does X still predict Y after we control for W and Z? Those kinds of questions. Like, is it this thing that's doing it or this other thing that's just a proxy? And most research questions are phrased in that kind of hierarchical fashion, so I want to teach you how to go about answering them as well. The last unit after that one then is moderation via interaction terms. It's one of my favorite things to teach. I love that. Do you know why? Because everybody thinks it's really, really hard, but it's not. Once you learn the algorithm, like, you can't unsee it. So I'm going to teach you the algorithm, and it will be excellent. All right, so you don't have anything to do right now for this class. You have reached the wonderful caught up zone. It's a mythical place. Enjoy it while it lasts. If you are behind on your homeworks, though, please take this week and catch yourselves up. As a reminder, I accept late work. I accept it up until the Wednesday of finals week when I cut folks off and turn in grades. So if it's late, that's okay. Keep working on it and send it in whenever you can. All right. Any questions or other things you want to chat about before we take off? How would we compare them? So the mean for the highest level would involve all of the fixed effects. The mean for the lowest level would involve only beta 0. So what we would have to do is add the betas for all 4 of these things together to get all the way from 1 up to 5. And it's that set of differences would be the difference between 1 and 5 in that case. Yep. Yeah, the coding table, if you work out like how the model gives you each level of an outcome being predicted, and then you can literally subtract between the two and see what's left. Yeah, good question. All right then, so I will be here for a little bit if anyone wants to chat. Otherwise, I hope to see you Thursday. I will let you know when example 4A and B are ready for you. Cool? Cool. Thanks for being here. Bye for now. Bye, Zoomers.